Good morning, welcome to the Lionheart Academy. This is Richard Tai. We're continuing our trigonometry lesson. Today we're talking about trigonometry lesson 57. We're moving on to the topic of complex numbers. Alright. So far we have been all working with real number sets, and then so right now I think we're going to move on from real numbers to something called imaginary numbers, and then I'm sure most of you have already learned about imaginary numbers before, so it's not a completely new concept, but let's just go ahead and review the concept of imaginary number before we go on in real numbers. So our number line, okay, since the beginning of our mathematical experiences, we have always been working with real numbers or the subsets of real numbers. Actually, starting from the very beginning, we start doing countings. When we first enter in counting numbers, we start with 1, 2, 3, 4, 5. We start with counting numbers, and those numbers are called whole numbers, 1, 2, 3. And later on we learned that there are something called a zero. Okay, we have a zero, and so we're starting with a zero instead of natural numbers. The natural numbers, we started with 1, 2, 3, 4, 5, the basic counting numbers that we can count from our fingers when we first started learning about numbers. And then later on we learned that there's a zero, so we have something called a whole number set, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we learned that there is a number beyond 0 on the other side, which is -1, -2, -3, -4, and so on and so forth. So now we have expanded our number set to integers. Then we worked with other numbers that are not integers. They lay between the integers. For example, between -1 and -2, or between 0 and 1, or between 1 and 2. So those numbers are fractions, and then so they actually give us real numbers. So we start to be going to the realm of all real numbers, and rational, irrational numbers, and they all add up to real numbers. So everything we have been dealing with is on this real number line. Okay, and there's certain properties about this real number line. For example, if you square any number, you will always get a positive number. If you take the square root of any number, okay, you can only take the square root of positive numbers greater than 0, or any numbers greater than 0. So there's no square roots for the negative number, because when we square a number, when we square any number, right, it will always be a positive number. It doesn't matter what x is. So x can be whatever number, but when you square x, it will always be equal to 0. It will always be greater than 0. Okay, so that means when we take square root, we won't be able to take a square root of a negative number, because if square root of x, okay, so let me go ahead and give you an illustration. So if a square is equal to 4, right, the square root of 4 will be equal to 2 and plus minus 2, right? Square root of a. Okay, actually I should say square root of a squared is going to be equal to a, right? But a can be either positive or negative. That's true. Okay, but a square root is always going to be a positive number. So when you take a square root of a negative number, then there's no number on this real number line that satisfies this equation. If I take a square root of a negative number. So for example, if I take a square root of a -1, there's no number that satisfies this equation, because 1 squared is 1, -1 squared is still 1. So we have square root of 1 equal to 1, or -1 plus minus 1, basically. The primary root is 1, but you can also do the negative root, so plus minus 1. But the square root of -1, okay, there's nothing in real numbers that can answer this equation. So therefore, we come up with something called imaginary number. Now, don't be fooled by the name called imaginary numbers. Think that it's not real. It's actually very real. Imaginary numbers, they're not imaginary in a sense. They're just not real. They're the opposite of real numbers. But they are they are as real, physically as real as possible. The things that we do, for example, electricity. Can we calculate currents? When we calculate resistance, we use imaginary numbers. Phase, signal transmissions, all those things has to deal with imaginary numbers. So imaginary numbers is very real in our life, in our society today. So imaginary number is that we have some kind of imaginary number unit. Okay, the imaginary unit I. Okay, and I is defined as this. I squared is equal to a -1. So this gives us the solution of what the things that we were dealing with the problem that we run into, is that we need to have a number whose square is a negative number. So I squared is equal to -1. So by definition, I itself will become square root of -1. So those are the basic definition of an imaginary unit I. This is different than the other I. But graphically, how do we represent imaginary units, okay, I? Well, before we were all on this number line, which is actually basically a one-dimension number line, right? It's a real number line, and then we start with a 0, and then we can go all the way to infinity, 1, 2, and then we go to negative infinity on the left hand side, -1, -2. But we don't have anything that can represent I. So what we do when you have trouble, we basically understanding the concept, understanding a problem, or representing a problem, then let's go ahead and expand our dimension. So instead of one dimension, now let's go ahead and go 2 dimension. So this is the imaginary dimension, the imaginary number dimension. And so instead of counting 1, we count 1i, 2i, 3i, alright, -1i, -2i, and -3i, and so on and so forth. So now we are going to do 2 dimension. Our number now has 2 dimensions, which is called a complex number plane. And this number, the combination of a complex and a combination of an imaginary and real number, is called a complex number. A complex number. So complex number is an algebraic sum of an imaginary and complex number. Imaginary and a real number. So a complex number is an expression consists of the algebraic sum of a real number and imaginary number. Alright, so what we're going to be talking about is we're going to be talking about the complex number. So a complex number has 2 parts, imaginary part and then the real number part. Okay, so we use a plus bi to represent the complex number, and a and b are all real numbers. A and b belongs to the set of real numbers. So a and b are all real numbers, but once b multiplied by this imaginary unit I, it becomes an imaginary number. Okay, so a complex number can consist of numbers that are purely real or purely imaginary, or a combination of both. So if I put this number here, for example, this is 2, 0, right? Which is 2 plus 0i, okay, 2 plus 0i, which is 2. This is still a complex number, okay? But if I go ahead and do 3 minus this number here, this would be 3 minus 2i. Why is that? Because it's 3 in the real part and minus 2i. This is just 2, okay? And then if I have a number here, which is just 2i, okay? And 2i is purely imaginary, but it's still a complex number. So all those numbers are complex numbers. As long as you can graph them on the complex number plane, they're complex numbers. And they can have a real number component, imaginary number component, or they may not have both components. But either way, this is a way that to help us express complex numbers. Okay. Now before we go on, let's go ahead and talk about I very quickly. Okay, just a review. So I is defined as negative square root of 1, which is just I, okay? And I squared is defined as -1, okay? And I to the third power is I squared times I, so it's -1 times I, which is just negative I. And I to the fourth power is negative I times another I, so it's negative I times I, so it will be negative I squared. But I squared is already defined as -1. So I to the fourth power is negative times -1, which is positive 1. Okay? And if we go to the I to the fifth power, is I to the fourth power times another I, so it's I again. And so as you can see, I to the sixth power is I to the fifth times another I, so it's I times I, which is equivalent to I squared, which is -1. And so I hope now, by the time now, you can see there's a pattern in terms of I powers. This is very important. So, and this power recycles in every fourth. Okay, every is a constant pattern. The pattern is every fourth power. You repeat the cycle. Now, let me show you what does it mean to multiply by I in our imaginary number plane. So this is the real number plane. This is the real number line, this is imaginary number line. This is called the complex number plane. So what does it really mean when we multiply by I? Well, when we do 1, okay, where our number is right here is 1, right? And then we do I, 1 times I is I times I is -1, I times I is negative I times I times I times I. Again, 4 of them is 1, so you come back, and then the cycle repeats. So basically, if you look at graphically, what we're doing is, when we multiply by I, we're rotating counterclockwise 90 degrees. Do you see that? You can see the pattern by just drawing this. Okay, so I do the first power, I do the second power, I do the third power, I do the fourth power, fifth power, I do the fifth power, I do the sixth power, I do the seventh power, I do the eighth power. So it keeps just going like this. So when you rotate, basically what happens when you rotate 90 degrees counterclockwise, that's what the meaning of multiply by I means. If you multiply by I, you're basically rotating 90 degrees counterclockwise on your complex number plane. So it's very much like what we're doing with our sine and cosine, and everything is related. That's why we're talking about complex numbers here in trigonometry, because it's very much related. And later on, as you can see, for example, the 3 minus 2i, we can also convert this to a different form called the polar form by writing out its magnitude, absolute value, and its directional angle, which is called, there's a name for that, okay? And so it's actually called modulus and amplitude. Yeah, we'll talk about that a little bit later, okay? Maybe in this video, maybe in the next video, okay? All right. Now, so let's go ahead and talk about basic operations for complex numbers. Okay, so complex numbers. Alright, again, complex numbers, we have the algebraic expression a plus bi. Okay, again, a and b are real number components. A and b belongs to the set of real number components. Okay, so a and b are not going to be imaginary for now. A and b are all real numbers. A plus bi itself is complex. You can have real number part, you can have the imaginary number part. Okay, so let me go ahead and just make sure I indicate that. So this is the real number component, this is the imaginary number component, and all together, we combine them together, we have a complex number. Alright, to combine complex numbers, alright, for example, so let's say we have 3 plus square root of negative 2. We want to combine that 8 minus square root of negative 8. Alright, so 3 plus negative square root of 2. Now, right now, this is not in the complex number form, and it's not in the a plus bi form. So let's write it in a plus bi. Now, square root of negative 2 is just square root of negative 2 times, okay, let me go ahead and do this, square root of 2 times negative 1, right? Okay, plus 8 minus square root of 8 times negative 1. So what you do is you factor out that negative 1, and you remember the square root of negative 1 equal to I, so this would become simply square root 2i. Alright, now sometimes we actually put the I in front of the square root 2, so we don't get confused whether the I is inside the square root or outside the square root. Now this one will be known as I square root 8, because negative square root of negative 1 is I. So it's square root of negative 1 times square root of 8, basically. Alright, now we can combine the 3 plus a, so we can have 11, and this is I square root 2. Now here, we can simplify square root of 8, which is 2i square root 2. So this will eventually become 1i minus 2i, so it's negative I square root 2. And this would be the summation of those two complex numbers. Okay. Now, let me go ahead and do another example. How do we multiply complex numbers? All right. So, how do we multiply complex numbers? Let's go ahead and take a look at this. First of all, we have two complex numbers: 2 plus square root of negative 9, and 3 minus square root of negative 16. Now, first of all, let's convert them to a plus bi form. So it's 2 plus 3i. Okay, why is 3i? Because negative 9 is 9 times 4 negative 1, and square root of 9 is 3, and square root of negative 1 is I. What about 3 minus negative 16? Square root of negative 16. Well, it's 3 minus square root of 16 times square root of negative 1. Square root of 16 is 4, and the square root of negative 1 is I. So in this case, we're going to use distributive property to help us. Okay. So 2 times 3 is 6 minus AI plus 9I minus 12I squared. Okay, so after I did this, I'm going to combine all the like terms. But I remember one thing about I squared. I squared is negative 1. So 6 minus AI plus 9I, this minus 12I squared turns into plus 12. Because I squared is negative 1. Negative 1 times negative 12 is positive 12. So I have 6 minus 8I, okay, plus 9I, minus 12 times negative 1. I'm going to write one more step here so you can see it. This is going to become positive 12. So 12 plus 16, 6 is 18. And this is going to be plus I. So the answer will be 18 plus I. Okay? That's our second example here. Alright. Let's go here and then let's see what do we do if we want to divide complex numbers using this called rectangular form. Actually, I've been using a rectangular form. So let's divide 4 plus 3i by 3 plus 2i. Okay. Alright, so how do we divide them? Well, in order to divide them, I have to put them in a fraction, right? Because fraction is division. Okay, so we do 4 plus 3i divided by 3 plus 2i. Now, in order to divide this, we have to consider something called the complex conjugate. Okay, let me write it here. Very good. Complex conjugate. You probably remember the complex conjugate here, okay, or any kind of conjugate. Conjugate, for example, a plus b, the conjugate would be a minus b, and this conjugate is very, very useful. The complex conjugate is for a plus bi would be a minus bi, and when we multiply the complex conjugate, the reason is it will give us a difference of squares, and when we have difference of squares, that means we will not have i's in there anymore, because once you do I squared, you have a real number. So let's multiply the complex conjugate 3 minus 2i on the numerator and the denominator. So the key is to convert the denominator into a real number. Okay, so and then how do we multiply? We use what we just did before. We use distributive property. So it's going to be 12 minus AI plus 9i minus 6i squared. Okay, the denominator is going to be 9 minus 6i plus 6i minus 4i squared. Okay, so as you can see, the I squared is going to be negative 1, so it's going to become 18 minus 1 plus 1 plus 1i. Okay, I just write I. The denominator, the i's, the term with i's will cancel out. So that's what's going to has to happen in order for us to have a real number in the denominator. And then it's going to be 9 plus 4. It's going to be 13. So this is the answer, or you can break it down into a plus bi. So it will be 18 over 13 divided by 1 over 13 times I. So this is my a. This is my b. The key is to multiply by the denominator's conjugate, so the denominator turns into a real number. Okay. All right. Now let's go and try another operation in which we have to go ahead and do a power here. All right. Let's try this. 5 minus I squared root of 3 to the second power. Now, when you raise a complex number to the second power, it means that we have to multiply by itself, right? Okay, so let's go ahead and see how we multiply by itself. So 5 times 5 is 25, minus 5i square root 3, minus 5i square root 3 again. And then here we have plus I squared times 3. Okay, I'm multiplying a little bit step by step. So negative times negative is positive. I times I is I squared. Square root 3 times square root 3 is 3. But I squared happens to be negative 1, right? So this becomes 25 minus 3. Minus 10 I square root 3. So altogether, 25 minus 3 is 22. Minus 10 I square root 3. Well, that's what you get after you simplify. Okay. All right. Now, how do we find the square root of a complex number? Okay. How do we find the square root of a complex number in rectangular form? Let's go ahead and try this. So let's see. We want to find the square root of negative 16 plus 30i. So how do we do that? Well, what this means is we have a number a plus bi whose quantity square is going to be equal to negative 16 plus 30i, right? Okay. So let's expand a plus bi. So a plus bi squared is a times a plus bi times a plus bi, right? A plus bi times a plus bi equal to negative 16 plus 30i. Let's go ahead and multiply this out. So it will be a squared plus 2abi minus b squared. Now why is minus b squared? The reason why it's minus b squared is because it's b times bi times bi is b squared I squared. B squared is positive, but I mean b times b is b squared. However, I squared turns into negative 1, so it becomes minus bi. Now take a look at this equation. We actually have two equations embedded in this one equation. We have the real number components. A squared minus b squared is equal to the real number component on the right hand side, which is negative 16. The imaginary number component, which is 2abi, is going to be equal to 30i. So 2ab has to be equal to 30. Okay, that means ab has to be equal to 15. So a times b has to be equal to 15, and a squared minus b squared has to be equal to negative 16. So this is a system equation we can solve. Okay. Now a minus b. So let's go ahead. A squared minus b squared is a minus b times a plus b equal to negative 16. All right. Now ab is equal to 15. So a equal to 15 divided by b. Now we can use this and plug this here, and we will have a quadratic formula that we can solve. So 15 over b minus b times 15 over b plus b. Well, I guess it doesn't really help us to factor this out. So let's just go ahead and leave it here like this. Alright, so it's 225 over b squared minus b squared equal to negative 16. We can go ahead and multiply everything by b squared as long as b squared is not equal to 0. Alright, so move everything to the right hand side and to the left hand side and make it positive. So it's b to the 4th power negative b to the 4th plus 16b squared plus 225 equal to 0. Let's make everything positive first. So b 4th minus 16b squared minus 225 equal to 0. It's a quadratic formula type of equation that we can try to solve it. So it's going to be b squared, b squared. Now 225, what are some of the factors of 225? Let's see. 225, we can break it down. Now I know it has to be, let's see, this start with 3. 225 divided by 3, 75. 75 divided by 3 is 25. 25 is 5 and 5, okay? So that's why it's 15 times 15, okay? Now, let's see if we can have 25. If we do 25 and 9, yes, 25 and 9 will come up to, will be able to combine to a 16. So it would be a negative 25 here and plus 9 here. Alright, so that means b squared plus 9 is equal to 0, or b squared minus 25 is equal to 0. So b will be equal to plus minus 5 here, and here b squared will be equal to negative 9, and b will be equal to plus minus 3i. Now however, we remember that a and b represents real number only, okay? So we are not going to take this I solutions. B cannot be a complex number in this case. B has to be a real number, which is plus minus 5. So that means AB is equal to 15, right? So if B is equal to plus minus 5, then A has to be equal to plus minus 3, okay? So the numbers A plus BI would be equal to now both of them have positives, their product equal positive, so they have to be the same sign. So it has to be 3 plus 5i and 3 minus 5i, negative 3 minus 5i. So those are the answers. They are the square roots of what we started with. They're the square roots of this negative 16 plus 30i. Okay, so as you can see, it's a little bit of a complicated process. We have to go through a lot of work to get to that. All right, so this is what we have done today. It's just introduction to complex numbers and some basic operations, how to multiply, add, subtract, and divide, and the power and roots of a complex number using rectangular form. We have been using rectangular form, which is a plus bi form. Okay. Next lesson we will go ahead and talk about other forms that we can use, trigonometry form or polar form of this complex number. Okay. All right. Let's. If you have any questions, please leave the question in your comment section, and we hope to see you next time. Thank you.